Yeah, we should do this more often. Start straight away with blood typing. Moving on with the blood chapter. It's exactly where we left off. This is an important topic to get. It'll be covered in a couple of labs. It'll be covered on the written portion of lecture exam 5. The next test.
Was that in the proctorio or is that here?
That's here.
Oh.
The written part is in class. The multiple choice portion is on proctorio. I don't like doing written online. I really do it in class. It's a little easier for me. Okay. Why do we type blood? Well, we're going to do a lab on it. But what you should understand clinically is when you transfuse patients with different bloods, you can have what's called a transfusion reaction or a cross reaction. When they first attempted this, they observed sometimes immediate or delayed agglutination. Hemolysis of RBCs occurred, leading to death. So it was soon discovered, well, obviously that's a problem, death. We're going to prevent that. So there are different reasons you want to give people other people's blood in emergency situations or chemotherapy patients. You have to transfuse people. Well, it was soon discovered that bloods of different people have different antigenic properties. These little microscopic surface molecules on your RBCs that can react with antibodies in the plasma of the people who receive your blood. And so the donated blood will react with the antigens on the RBC surfaces of the donated blood. So here's a table of the blood types, and by population group. You don't have to know the numbers. You just know that some types are rare. We're going to go through all the blood types here. I think what's important for you to understand in biology class is how cross reactions occur. So let's remember when you fractionate blood, the antibodies that protect your body from all non-self cells are in the plasma component. Usually when you donate blood, at least in this lecture, you donate the crit. You donate the RBC, the oxygen carrying capacity of the blood. So that's what I say up here. Donor's blood, donate only the packed RBCs. So that way you're not donating all the antibody, or you just donate this part, okay? Just keep that straight in your head. So that when you donate blood, that's what you donate. But when you receive blood, we are concerned with the antibodies you have, because we don't want your immune system attacking the blood we're transfusing into you. Okay? I mean, that's what your immune system is supposed to do. It's supposed to fight anything that it recognizes as non-self. Okay? But in this case, we're trying to bypass that because we want you to receive someone else's blood for medical purposes. So, that's what I say here. If you type a person's blood, it can prevent transfusion reactions. The donor's blood is attacked by the recipient's immune system. Okay, so we call those molecules the antibodies or agglutinates. That will cause agglutination. Just look at this list of things. Basically, these are the things that can lead to death. You're receiving so much of that blood that it's just going to cause too much problems in your circulatory system. And here's a picture of it, a picture of agglutination. So if you're a person, a designated donor, and they draw the red blood cells as having these surface antigens on them, these little blue triangles, which symbolize self. So in your own blood, you will not have antibodies that attack yourself. That's called an autoimmune disorder. something's wrong. So let's say, for example, you may have antibodies against other things that fit other shapes. Say, for example, a circle antibody. I'm using shapes as to symbolize different varieties of antibodies. Or maybe you have a square-shaped antibody to fight any other non-self cell or pathogen that can fit that shape. But you don't have things that can attack yourself. That's the point. But if you have another person who we'll say is the recipient in this example, so maybe their blood has different antigenic profile. I'll use a different shape. Let's say, for example, little orange balls. It's a different blood type, is what I'm trying to say. People have different blood types, and this type is different antigenic markers. But maybe they do have the antibody profile that includes one that will attack this blood. So if this blood from the donor is then infused in the recipient, this different blood type, let me use the same color, blue triangles. You see the problem. This antibody will attack that blood. Well, it'll cause that. It'll cause a cross reaction. Okay, and this is the thing that can lead to death. So, what was the concern for the recipients? Was it their red blood cells, or was it their antibodies? It was their antibodies. Who cares about that's their blood. For whatever reason, they need other blood, and that's why we type blood, so we don't have a cross reaction. That's what I'm supposed to teach you to do. And so donating blood is okay if ... If the donor's RBCs do not have antigens that will react with the recipient's antibodies. So I kind of color-coded with purple. And purple is the RBC right here, okay? The antigens that are on the donor's blood when the recipient receives it, there's nothing in the antibody profile that will attack the blood they receive. That's all you're trying to do. It's easier to understand if you kind of like map out all the blood types. All the blood types are based upon 3 different antigens that we test for. And there's dozens and dozens of antigens. But these 3 that I'm going to present seem to be the ones that cause the most problems in transfusion reactions. Okay. So let me go through all the blood types, and I don't like to use this figure because it doesn't include all of them, all the systems. The blood typing systems, the main ones that are presented in a basic class, it's more complicated than we present in A&P. But I think many students have enough just getting this. We call this the ABO system for different blood types, which includes type A. That simply means the A antigen is present on the RBC. The A antigen is present. So let's say that on the RBC, I'm going to draw triangles. Let's say a triangle represents, in this lecture, a antigen. But that an antibody that fits that shape would represent an antibody against A, or anti-A. I'll just say, I'll write it out. Antibody against A. Your antibodies are your simplest ammunition against pathogens. Okay, so let's say that you have type B blood. Type B blood means the B antigen is present. Okay, so how about I use like little circles on the RBCs to symbolize that. So a circle represents the B antigen, and a circular shaped antibody represents the antibody against B. I don't want to keep writing it. I think you kind of get the idea. Well, let's talk about type O. Type O means A and B antigens are both absent. Both not there. Don't got it. So it's not type O is not an antigen. There's no antibody against it. It's just not there. That's what it means. ABO, that's it. Okay. Now we combine this with another type, but just let's take an inventory. How many antigens do you have to keep track of so far? Just 2, A and B. However, the RH system there's a whole slew of RH antigens. Usually the one that, when I say RH, I'm referring to type D. If you ever see the letter D, I usually just go with RH. In this system, they don't say type RH. They just use plus or minus. If you're RH positive, a positive simply means the RH antigen is present, just like before. RH antigen is present. So on my RBC, let's use squares to symbolize that antigen. So square means the RH antigen. And an antibody that fits that shape is the antibody against it. Okay, so then what does RH negative mean? I'm not trying to trick you. RH negative means the RH antigen is not present. So now how many antigens do you have to keep track of? 3. Which ones? The A, B, and the RH. Okay? You put them together and you can come up with 8 different types that you have to know. Start with A negative. Type A negative. So what does that mean? Go through the thing where you think about the antigens that are present on RBCs and assume they have all the other antibodies. Not the, okay, let me just do it. Okay, so if you're type A negative, of the 3, there's only one antigen that's present. A. Oh, I erased my key. I was using triangles, right? So what you can assume in their plasmid profile, they're going to have antibodies against B and RH. Okay, you should just assume that in your patients. They may not have it, just assume they have it. Okay? If you assume they don't have it, you're gambling with their life, right? So that's why we just say they have it. All right. Type A positive. There's 2 antigens present. Which ones? A and RH. So I'm going to draw triangles and squares. And I'm going to draw in their antibody profile the antibody against B. Okay, you start developing these antibodies very early in life. I've heard that like when you start eating food, you start to develop some of these other antibodies. You're exposed. How you develop antibodies is you're exposed to the antigen and you make antibodies against it and they stay with you for life. Did you get your flu shot yet? All of you ought to get it. What are you getting when you get the flu shot? They give you a little bit of antigen from the virus or whatever they think is going to come around this season. Your arm is sore for a few days because you're building antibodies. You're having a reaction. You're building up antibodies against everything they shot in your arm. Anyways, that's what antibodies are. We're just talking about for blood typing. Let's do B negative. One antigen present, just the B, type B, and we'll use circles, is that right? Yeah, circles. And assume that they have the antibodies against A and RH. Anti-A, anti-RH. Alright, type B positive. That is going to have the B antigen, the RH antigen. So I'm going to draw circles and squares. Circles and squares. And they would have the antibody against A. Then you have type O. O neg. O means A and B are absent. Negative means RH is absent. So all three are absent. But you should assume that all three antibodies are present. The one against A, the one against B, and the one against RH. O is called the universal donor. Maybe you've heard that. Well, amongst humans, okay? You can donate to any type. Now, what makes this person a good donor? What do you donate? What fraction of blood? The crit. So why does this make you a good donor? There are no antigens that could be attacked in the recipient. You put that blood in, there's nothing, yeah, it's all good, okay? But what if you need to receive blood, who can you get it from? Only other O negatives, that's it. Anyone else is going to have one of the antigens that you may attack, okay? So that's the thing there. So here's O positive. O positive is, well, just the RH antigen present, but you'll probably have antibodies against A and B. There's another rare type called AB, type AB. It's very rare. Look at the table to see. AB negative would be you have the A and the B antigen both present. So I'm going to draw triangles and circles. You probably have the antibody against RH for that type. The last type is type AB positive, very rare. You can Google the prevalence. I showed you that table, but it's very rare, but let's just know it. You have all three antigens that we're talking about present, the A, the B, and the RH. So I'm going to draw the triangles, the circles, and the squares. But then no antibodies against those three. So I'm going to write no antibodies, no ABs against antigens A, B, or RH. So they call this blood type the universal recipient. This person, very rare, can receive blood from anybody. Why? no matter what blood they receive, there's no antibody to attack. Okay? Think of antigen as antibody generator. Okay? I know it gets confusing with the anti-anti thing, antibody, antigen, but that's what this means. That's what this means, antibody generator. So you receive any kind of blood type, it doesn't matter, they don't have antibodies. It's not that they have no antibodies. They have no antibodies against three things. I'll keep that clear. A lot of times students write about this on exams, and I always ask about the universal recipient. And you just say, well, they have, you start talking about the wrong thing. Like for example, oh yeah, the universal recipient, they have all the antigens. And you stop there. Now why is that answer insufficient? Why are you a universal recipient? It's not because of this. It's because of this. And then you say, oh yeah, the universal recipient, yeah, they have no antibodies. And you stop there. Now what's wrong? Why is that insufficient? You don't say against what? You have no antibodies. It's terrible immune system. And I think you need to say. But whenever I have to like say, I think they meant that, you're losing points. I don't know what you meant. You have to tell me. It's a test of your knowledge. So be very complete in how you answer. And students who are not specific in how they answer these types of questions, it's very clear to me in the context of the exam. Okay. So let's kind of go through the thought process. You know, how do I solve these blood taping problems? Now that we know all the types. You know, I was doing some research for this lecture. You know, mistakes are made a lot, either by blood banks, by the hospitals. They type the blood wrong. You know what the number one mistake is? It seems kind of silly. You just misidentify the patient. You don't know it's them. You give it to that's like 40% of the mistakes. Okay, so anyways, let's say we have a simple situation where one person is giving to another person. John and Peter. John is type AB negative. Peter is A positive. And you always have to designate, well, who's the donor, who's the recipient? John's the donor. So I always go through the exercise myself. Okay, how do I figure this out? Can John safely donate to Peter? That's the question, right? Because we called one donor, one recipient, so we know who's who. And which antigens are present in John's blood type? The A, the B. What about the RH? No, because he's negative. So I want to draw my triangles. What other shape is for the B? The circle. These are circles. Thank you. All right, I'll just make sure you're with me here. Now let's just kind of complete the exercise here. Okay, so what antibodies does he have? Probably the ones against RH. If you're A positive, you have two antigens present, the A and the RH, so I'm going to draw triangles and squares. And the antibody he would have is the antibody against what? B. So I want to draw like a circle on. Okay, so that's the situation. And to go through it, what I did was I created questions that is the correct logic to go through to solve this correctly each and every time, no matter what the question is. So how would you, what would you consider first? Which choice is correct? A, B, C, or D there? John's the donor, Peter's the recipient. When you think, commit yourself to an answer, write it in your notes, or write something. Don't keep it in your head. Because when I tell you the answer and you're wrong, you can't deny it. You might be right. Did you choose B? B is correct. You consider John's antigens Peter's antibodies. Who's the donor? John. Now, what do we donate when we donate blood in this lecture? The crit, the red blood cells. We consider the antigens, the A and the B, the circles and the triangles.
Can you spell crit real fast?
CRIT, short for hematocrit. In Peter, he's receiving blood. We're worried about his antibody profile, right? Because when he receives blood, we don't want anything to attack it. So, okay, well, let's see. So, so I already mapped it out. So the next question is, can John donate to Peter for John's blood type? He will have, what did we draw? Which choice is correct? Think about it. Commit yourself to an answer. Write it down, and I'll tell you. B again. A and B antigens on his RBCs. That's what we drew over here. Okay? With that. For Peter's blood type, we're concerned with his antibody profile. Which choice is correct? The one that says only B antibodies in his plasma. That's choice D on this list of choices. Okay, it's not that this is where we're going. Okay, here's the problem. So if Peter receives this blood, with the triangles and the circles, Peter's B antibody will attack it. John cannot safely donate to Peter. Okay. So let's look at the choices here. Let's first get the yes, no. Can John safely donate to Peter? Is that a yes or is that a no? Okay, that's a no, but then the logic is also expected. What cross-reacted? That's kind of what we look for here. Well, it looks like John's B antigen reacted with Peter's B antibody. Okay, but that's how you want to word it. You just put what cross-reacts. No, but why? You're expected to know what cross-reacted. You can't just say something generic like, well, yeah, John's blood reacted with Peter's blood. That doesn't tell me anything. You have to tell me which of the three cross-reacted antibody antigen. Okay. So let me give you an opportunity to try one. You do Betty to George. I'll give you a couple minutes. Just go and talk amongst yourselves. See if you can do it like I did.
positive, then I'm maybe not
You can get anybody to it.
I can get anybody because there's no antibodies against
All this stuff.
no antibodies against
So an estrogen is what? What is it? What does that mean?
All right, what'd you get? It's a no.
yes.
Anyone want to volunteer with thinking what cross-reacted? What antigen is present in Betty? A. What antibody is present in George? That is what would cross-react. So it's very important that you go through this stuff. I saw some people try, and some people didn't. Usually that's why I give an oral quiz for the lab on, because you have to stand in front of me and say something, so then you can't hide, right? Always put yes, no, and then what cross-reacts, and you're in good shape. Let's review what we said about the universal recipient. What made them a universal recipient receive any blood? No antibodies. Yeah. And what made you a great donor? Yeah, no antibodies. You'll have a chance to talk about blood typing again on Friday and on Monday and on the written test. So I'm gonna make sure you guys get it. That's one of the essential components for this unit. Look at this table. Let's see what we can learn from this generalized table. So if you look at the top, you got all the blood types. If you look at the side, you got all the blood types. And you just label donors and recipient. And what can we learn from this? A check means safe to donate. Okay. Right there. So one thing that's simple is people of the same blood types can give to each other. I think that's easy enough to understand. Okay, so you know that's okay. Okay, let me ask you this question. Can positives, just talking about RH and nothing else, donate to negatives? Yeah, at this point in the lecture, people are still learning. You're always going to hear A, B, yes, no, and you're both. So you guys are trying to work it out. Let's see how the table. Here are all the positives. Here are all the negatives. I see this big vacuum. No. But why? It's always the same reason. Not even considering the A, B, just consider the plus minus. If you're plus, what do you got? Antigen, which one? RH. Just RH. Just talking about RH. You're RH positive. Okay, so if you're RH positive, you have the RH antigen. Is that clear? Okay. If you're RH negative, do you have it? Do you have the RH antigen if you're negative? That's a no. But what antibody would you have if you're negative? You would have the antibody against RH. So, what's the problem if a positive donates to the negative? That blood will be attacked by that antibody. And that's always the case. Okay? So let me reverse the question. This answer is a no. because the Rh antibody in a person who's negative will attack the Rh positive blood. The other question is, can negatives donate to positives? Let's answer the question first by just looking at the table. Oh, here are the negatives. Looks like you got a lot of check boxes for the positives or the negatives. So yeah, that's positives. If you're negative, you can donate to positives or negatives. So the reverse is a yes. If you're the donor, if you're Rh negative, you don't have that antigen. So why is it okay to donate to positives? They're not, it doesn't matter. Like, even if they have the antibody against Rh, they're not going to attack it. So that's why you can donate to positives or negatives. The antigen that's being donated isn't there. So there's no cross reaction just for Rh. Okay, so that's one generality that I like to point out on this table. Here's another one. Look at the type AB positive. Why are all these boxes checked? Check, 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 check. You can receive from any type. Universal recipient. They have no antibodies against A, B, or Rh. Why is this checked from top to bottom for O neg? Universal donor. But why? Well, no matter who you give blood to, you don't have the antigen A, B, or Rh. Okay, so when you do the blood typing lab, this will be on Monday, by the way. For Monday, I'm going to give you like 4 unknowns. In a clinical situation, they roll the guy in on a gurney, he's unconscious, maybe he needs blood. You got to know what type he is, so you don't give him the wrong type. So how do you do it if you don't know? You can't ask him, he's unconscious. Maybe if he was conscious, he doesn't even know. So you just take his blood to the lab, and this is what you'll be doing in the lab. Just type 4 unknowns. For example, let's do number 1 together. Type unknown. What you're doing is you're testing for the presence or absence of the antigens, the A, the B, the Rh, because then you can type it, right? Type, well, let's say test. This is a test. Test for the presence or absence of A, B, and Rh antigens. Because you don't know. So what you do is in your lab, you keep little vials of antibody A, antibody B, antibody Rh. You have it on the shelf in your lab. You're the lab tech, let's say, just to pretend. And you get your well, number 1. And you put the patient's blood in it and you're testing. So that's step 1. Put the blood in the well. And for our blood lab, our unknown blood is basically fake blood. Okay? We don't use real blood anymore. Okay, so then to test for example, the presence of antigen A, just add antibody A. Add, what shape did I use? It wasn't a circle, it was a triangle. So add antibody A to the well and see if anything happens. Because if the antigen is there, it's going to clump up. It's going to agglutinate. But let's say you add it and nothing happens. It's negative for agglutination. No agglutination. What conclusion do you reach? Interpret this result. This is one of the questions I asked on the roll quiz. Oh, you put negative for that. What does that mean? And you say things like, It's negative. Yeah, I know, interpret the result. Oh, it means it was negative. What does that mean? It's got to mean something. What I would say is, comment on the A antigen. Is it there or isn't it?
No.
He's not type A. A antigen is absent. That's all you got to say. That's what that means. Oh, he's not type A. Let's move on to the next one. Add anti-B. Looks like you got a reaction. Wait, stir it up. Well, look, it's all clumping up on me. Huh. This is positive for agglutination. What conclusion do you draw? The B antigen is present. So at the very least, you know he's type B. Okay. Let's do the last one. Add RH. Look at that top result for number 1. Is that positive or negative? Negative. Negative. No elimination. So what the conclusion is, RH antigen absent. This guy's person is B negative. That's the type. Take about 30 seconds and type 2, 3, and 4. It should take you 10 seconds per if you understand what's going on. 2, 3, and 4. Go. Ding dong, time's up. What'd you get for number 2? Two. No agglutination, no agglutination, agglutination. O positive. Number 3. B positive. Number 4. Negative for all 3. O negative. Let's have a show of hands. Yeah, I'm kind of getting this. About half. That's about right. It's a process for some. You'll get there. You know, some people walk in late. What the heck's going on? So we have YouTube. We can go and practice later. Here's a clinical situation. It's called, what's not good, erythroblastosis fetalis. So let's say mom is Rh negative. It's pretty rare to be negative, actually. But father's Rh positive, so baby's Rh positive. And well, at birth, there's a lot of bleeding, some hemorrhage, and maybe mom is exposed to Rh positive blood just a bit. Okay, now baby's fine. Baby's gone. It's during delivery. But now, over time, mom being exposed to Rh positive blood will now develop antibodies against it. Second pregnancy, assuming it's also Rh positive, those antibodies can cross the placenta, causing problems. Now, obviously, they screen for that, okay? So it's not a problem, but if it were to happen, that's the condition, erythroblastosis fetalis, when the Rh antibody crosses the placenta in Rh positive blood for the baby. Okay. The physio X, I don't assign that anymore because I kind of talk about everything in lecture. So I do want to move on to the next batch of slides, which cover these topics. So for those of you who print out the slides and bring them to class, it's the ones with these topic headings. We'll start with formation of blood cells. So I'm changing gears real fast. I have a lot of ground to cover. All right, the hemocytoblast cell, the bone marrow. What we're talking about here is, well, let me remind you what we talked about before. We talked about the formation of red blood cells in the bone marrow. We talked about EPO from the kidney targets the bone marrow, and you go through all of those blast stages like the erythroblast, normal blast. Reticulocyte, and you get your mature red blood cell that enters the circulation. Okay. Platelets. Platelets require TPO. Full name is thrombopoietin. It's on another slide. I want to write it out. TPO. Go with that. There's a cell called the megakaryocyte. Huge cell. Anyways, little flakes flake off of this big cell and enter the circulation. We know them as platelets in the blood circulation. Or thrombocytes. Let's just call them platelets for now. They all are derived from the hemocytoblast. This next slide shows how the hemocytoblast forms all the white blood cells. But just to give you some numbers, the bone marrow is putting out billions of cells every day. And you don't have to know the numbers, but what I do want you to know for the bone marrow, that's a slide of bone marrow, is how the white blood cells are formed. So what you see here in red marrow is all the little purple cells, the cellularity forming the red blood cells, the white blood cells, the platelets. You see these pockets of white, which are adipose. And as we age, the adipose increases and the cells decrease as we age. So here's a slide showing the formation of all the white blood cells. So they're all still derived from the hemocytoblast. What we see in these top columns here, the hemocytoblast, they form all of these colonies called granulocyte, monocyte, colony-forming units. So from the hemocytoblast, we get these granulocyte, monocyte, colony-forming units. Sometimes I abbreviate that GM CFUs. Okay. Now, on the slide, I have GM CSFs, which the SF is a stimulating factor. I'm not going to write it out. Stimulating factor. The trend here that I'm hoping you're seeing is you need these different factors to get the blood formed. You need APO for what? The RBC. You need TPO for the platelets. You need this one to get your white blood cells. Once you get these colony-forming units, what you should see is that on this arm over here, all of these cells are forming one of the granular leukocytes. So out of these colony-forming units, on the one hand, you're going to get GCSF, which stands for granulocyte colony stimulating factor. I'm saying slow because I'm not going to write it out. What's the S? Stimulating. What's the F? Factor. Okay. And well, basically, you'll get out of the colony forming units, what's listed on the slide here: eosinophils, basophils, neutrophils. Those are your granular leukocytes. So let me just write those names on the board. Eosinophils neutrophils, basophils. That's what you would see in the circulation in a drop of blood. Now, also coming out of those GM-CFUs, under the influence of MCSF, the M is monocyte. Monocyte, colony stimulating factor, you're going to get your monocytes, which are agranular. Monocytes can become macrophages when they're attracted to an area of infection. And they'll leave the blood, they'll enter the connective tissues to fight infection. Macrophages. So this is basically how the blood cells are formed. The one I'm not going to cover now are the lymphocytes, because I have a whole lecture on them next week. So I just wanted to kind of at least show you all the other blood cells formed. You should be able to recognize the white blood cells on an histology slide. And there's a nice little panel of it, right? Remember I gave you the little memory jogger, never let monkeys eat bananas, which refers to the prevalence of the white blood cells. That hadn't been said. Which are the most numerous? Neutrophils. First listed, the most prevalent. So if you're looking for these cells on a drop of blood, which one's going to be the hardest to find? Basophil, the one listed last. And in fact, our entire slide collection, I think 1 year, I had one student find one. That was it. They're hard to find. Okay, well, let me give you some basic functions on how to identify and what they do. Neutrophils. Where is this? Neutrophils. How would you describe this color? I said purple, light, pale lilac. I'm copying it from a book. Whatever you think that is. They take up that kind of stain, that nice purplish, bluish, whatever it is, color. And what I think is interesting about the neutrophils, I don't know why, but they have these multilobular nuclei, right? It's not just a round circle. It's like multilobular nuke. Their function is phagocytic. They're good phagocytes for us. I mean cell eating. Phagocytes. I'll just kind of list that as the two major things to know. These are one of the granular variety. The granules have defensive molecules in them. Can't see them too much in the cytoplasm on this slide. Let's move on to the next one. Eosinophils. Eosin means red staining. Eosinophils. Look at that nice red bilobed nuke. Exactly 2 lobes connected in the middle ever so slightly. Okay. The red granules are very apparent when you see this under the scope. Usually students misidentify neutrophil, I think it's eosinophil, but when I find the red one, and I have the students always react the same way. It's like, wow, because the redness really jumps out at you. Red staining, granules. Usually, if you have an elevated amount of eosinophils, it might mean you have some kind of parasitic infection. Parasite. They usually fight parasites, like a tapeworm in your gut. Usually not a problem in westernized states, but yeah, they're out there. Eosinophils. Okay, what's next? Lymphocytes. On Monday, I'll give an entire lecture on the lymphatic system. For now, let's just kind of learn what they look like. Not much to look at. Just a round cell with a round nuke. Very dark and purple. I'm using black, but the nuke is so big, you just barely see a rim of cytoplasm. Okay? Now, when they become activated, they'll increase the cytoplasm, but that's what they look like. Huge nuke, little rim of cytoplasm. I'll talk about the function later. Okay, the monocytes, those are the ones that become macrophages. That's their main thing. The monocytes. They become macrophages. When I was a grad student, they abbreviated macrophage like this, because that's the that sign means phage. Anyways, the macrophages are also phagocytic. They have this kidney-shaped nuke. If you can look at the picture there. That's how I identify them. Kidney-shaped nuke. And you can't tell by looking at these slides, but the monocytes are the biggest. They're the largest of the white blood cells in terms of diameter. The last one is the basophil. Go back over here. The basophil, well, you can't see the nuke. The dark staining granule stains so dark, it obscures the nuke. You can't see it. Dark staining granules obscure nuke. That's how you know you're looking at one. These secrete histamines. Why are you taking antihistamine? You're draining, you're running, there's some allergen in the air. It's these guys. You're trying to fight the allergen by secreting these molecules. Make the tissues secrete fluids to flush out the allergen. Okay, that's kind of annoying. So you're taking antihistamine. All right, so that's a basic idea of what each of those cells do. I'm going to shift gears once again. The other thing about blood we want students to know is how it coagulates. And it's kind of a different topic altogether. And the picture I have is a picture of blood coagulation. Not to be confused with agglutination. Agglutination was when the antibodies attacked the donated blood and it all agglutinated, clumped up. This is a clumping up too. However, look what you got here. See the little fibrin threads? When those trap all the blood cells, that's coagulation. And that's the goal. That'll help stop bleeding and prevent shock. Shock is a lack of blood flow. And you can have that for a variety of reasons. And I have some causes of shock listed on the following slide here. Now, a myocardial infarction, acute MI, that's when the heart muscle dies. But that's got nothing to do with blood. Why is that a form of shock? Well, because what does the heart do? It pumps the blood. So a damaged heart can't sustain enough pressure, that could lead to shock. Let's say you have a brain injury. The brainstem is damaged, the part that causes the sympathetic efferents that we talked about in the baroreceptor reflex. Vascular or neurogenic shock. You know, these like, maybe you've had experience, you test for the pupil dilation, right? Or the pupil constriction. If the pupils are fixed and dilated, that means the cranial nerve is damaged. The cranial nerves come off the brainstem. So if the cranial nerve is damaged, you might think that there's some brainstem damage. If there's brainstem damage, you got a problem because it's the sympathetics that come from the brainstem that help constrict your arterioles, right? I think I said T1 to what, L2. And if you can't vasoconstrict, they'll dilate. All the blood will leave the arteries and sit in the veins away from the vital organs. That could lead to shock. You can't constrict, you can't keep the blood pressure up. Of course, the most obvious way is you're just losing blood. The most common cause of shock. Okay, so, and I even talked about how pressure starts to drop, right, after you lose a certain percentage of blood. I'm trying to teach you the process that can prevent all this. Hemostasis is usually taught in these 3 steps. A vascular phase, a platelet phase, and the coagulation phase. This is the most important part. This is number 3. And I usually teach them in order. They may not necessarily occur in that order when you have a broken blood vessel, but we do present them that way. So let's say you got a break in a vessel. The first reaction is that the damaged vessel will spasm. Blood coagulation, vascular spasm. I want you to think of the 2 nicks. TM, no, TI, TM, TA. Remember that? Well, it's a good reminder because, you know, you got to take is there a test on blood vessels? I'm being sarcastic. Of course it is, right? What's it do? All right, so you know that. Test on canvas. Blood vessels tomorrow. Well, anyways, which tunic had the smooth muscle cells? TM. TM. So that is what spasms, and causes a vasoconstriction that minimizes blood loss. That's shown better on this picture there.
Should I tell you there's a hive in the
Is there another wasp in here?
Yes.
Mm.
It just came out from that hole. Oh, yay.
Oh, I left? Hey, thank you. See you. Yeah, I have spray and swatters if they come back. Yeah, we gotta take care of that for you guys. All right, minimizes blood loss. Well, you can see why it minimizes blood loss. Look at the spasms. You can help by applying pressure, right? Because remember that if you decrease the radius, it affects resistance to blood flow quite a bit. So that's why you apply pressure to a wound. It helps minimize the blood loss. So that happens. And well, the other thing that happens in the damaged vessel is a platelet plug may form. Platelet plug formation. Now I have different pictures of this. But let's talk about platelets a little bit. The thrombocytes, or platelets, I said earlier, are derived from the megakaryocyte. And it's already in your notes, but do you recall TPO? That stimulation will get the platelets to flake off the megakaryocyte. Basically, they're just packets of cytoplasm that flake off the megakaryocyte. And that is what enters the circulation. You can see on the drop of blood. So the megakaryocyte, we're concerned with the platelets really that are in the circulation. So they don't have a nucleus. They have most other organelles. They're just packets of cytoplasm, but they have a very well developed cytoplasm. Because what do they have to do? They got to clump up and plug the leak. So it's very important that they have that so they can stick to each other very well. So they have a lot of adherent capability. They also transport a lot of chemicals important for this process. So here's a picture of activated platelets stuck in a fiber mesh. Okay. So there is an activation process, and on a drop of blood, they look like tiny, tiny purple fragments. If you're sitting in the front, you can probably see it. If you're sitting in the back, you're not going to be able to see it. But let me point it out. See a little fragment right there, and there, and there. Little fragment. Okay, then there's a, ooh, that's a nice monocyte. There's a neutrophil. But anyway, little fragment there, that's kind of what they look like. Here's kind of a better picture for presentation. Unactivated, activated. Oh, big and spiky on you. So there is an activation process that they go to. What's going to happen is you get a break in a blood vessel. Blood's flowing by, and the platelets would adhere to the exposed collagen fibers of the underlying tunics. Platelets bind to collagen fibers. And basically, that's when they become activated. When they become activated, okay, let's say this little fragment is unactivated, so they get all big and spiky. That's activated. You increase the membrane proteins so they can stick to each other and plug the leak. They also secrete a myriad of chemicals to cause a positive feedback loop to attract more platelets, to secrete more chemicals, to attract more platelets until the leak has been plugged. So they secrete things like ADP, serotonin, thromboxane A2. These are chemicals that will facilitate more platelets to come. So we call this a positive feedback. Because what we're going to do is we're going to enhance the original stimulus to get more platelets, to secrete more chemicals, and we'll just keep cycling until you get a nice flow. So not only does the activation process involve a change in shape, it involves secretion of these chemicals that facilitate more aggregation and vasoconstriction. Here's a better picture of these processes. Step 1, vascular spasm. Okay, the cells were, of the tunica media, the smooth muscle cells. So do you see here in this sectional view, these cells are not contracted. You want the smooth muscle cells to contract. That helps kind of plug the leak, not completely, it leaves a little gap there. So what this picture shows in this break is that these activated platelets are bridging the gap, so to speak. Okay. These are kind of aggregated, maybe not yet activated, but these are activated. So when I say release of chemicals, it's those chemicals that you got to know. And it's causing more positive feedback. The other thing to note here, you want to restrict aggregation only to the site of injury. Okay. And so what happens is neighboring uninjured endothelial cells will secrete prostacyclin and nitric oxide to restrict aggregation only to where you need it. Neighboring uninjured species restrict aggregation to injury site. By secreting prostacyclin, nitric oxide, NO. Okay. And those are the endothelial cells of the tunica intima. So a platelet plug is kind of a temporary stopgap. Does a good job plugging it. And what we got to get to is the true coagulation. Let's get to the fibrin mesh, step 3, true coagulation. This fibrin mesh forms, well, happens to be 3 steps. So step 3 is 3 steps right here. Intrinsic and extrinsic pathways, and then a common pathway to fibrin. The platelets of the plug, they're loosely knit, but when reinforced by fibrin threads, they become a strong clot. So it's all about the fibrin threads. Here's a picture of fibrin threads, little bit in an intermediate stage, late stage. So take away from this, you get some fibrin threads fast. You get some later on that help reinforce. So you want to stop the bleeding fast in that intermediate stage. So let's look at intrinsic, extrinsic pathways. Based on number of steps, which looks faster? Intrinsic or extrinsic? Extrinsic is faster, there's less steps. So it gets you a little fibrin more quickly. Okay. The one that requires more steps may take a little bit longer. So let's learn both pathways. We'll do intrinsic on this side. Extrinsic over here. Now the extrinsic pathway, it requires vessel damage, some kind of tissue trauma. Well, when you damage a vessel, what happens is the flowing blood sees the tissue factor. Normally that doesn't happen, but injured cells secrete tissue factor. Flowing blood sees tissue factor. It's a clotting factor. Clotting factor 3, or I just abbreviated TF sometimes. Okay, and this pathway we get kicked off, but it requires vessel injury. Now the intrinsic pathway does not necessarily require a vessel to be injured, because let's remember that if you just take the plasma and leave it on the bench top, those clotting factors can just react with the charged ions in the glass tube and cause a clot. So it doesn't really require that. But for this example, let's pretend that there is a damage to the tunics. So let me just draw a continuous line there and put a break in it for both. Because both are happening at the same time. They just use different cascades. So let's kind of like simplify by skipping to this part right here. These are the complexes that form that are very important. For the extrinsic pathway, the tissue factor, it complexes with factor 7, VII. You gotta love those Roman numerals, right? Okay, look at page, well, you don't have to look now, but refer to page 661 in your book. It's got a table of all the clotting factors, most of which I'm presenting. It's like the cranial nerves. You got the name and the number, right? The Roman numeral thing. 661. Well, anyways, the extrinsic pathway, the tissue factor complexes with factor 7, VII. Now, it's important that calcium helps this process occur. And what that does is it activates a very important factor 10 to this area of infection. Factor 10. But before we get there, let's go back and look at the other side. Happens a little bit more slowly. 9 complexes with 8. IX, VIII. Okay, so that complex, it took some work to get there. If you look at the cascade of events, you had to go 12 to activate 11, 11 to activate 9. You also needed calcium. So there was a few more steps there. So you had to go 12 to get to 11. And it looks like 11 with calcium was able to activate 9. I want to throw in calcium there too. But once you get both of these complexes formed at the injury site, you're localizing the effects of factor 10 to this area. I'm going to draw an arrow in here, and here, well, because now we're kind of like merging onto this common, what's known as the common pathway. Okay, factor 10. Once you get to factor 10 will activate prothrombin activator or prothrombinase. And that's our common pathway. prothrombinase. So, extrinsic, intrinsic, from here on out, common pathway is what we call it. Why? It's common to both extrinsic and extrinsic. They both get the factor 10, right? So, the extrinsic pathway, this is kind of a summary of what I'd said already. Just think of it as a shortcut to factor 10. We said it's faster because there's less steps. Okay? You get a little bit of fibrin quickly, later reinforced by the intrinsic pathway. But both are basically localizing the effects of factor 10 to the area that is injured. So this common pathway, I called it prothrombinase. Prothrombin activator is also an acceptable name. But what it's doing is it's going to convert prothrombin into thrombin, which is clotting factor 2. Prothrombinase converts prothrombin into thrombin. Thrombin, that's your activated form. It's clotting factor 2. Remember, all these got a name and a number. Well, anyways, clotting factor 2 will then activate fibrinogen. Fibrinogen is the inactive form. The thrombin will activate that into your fibrin threads. That's your little spider web of blood coagulation that I showed you prior. Okay. So that is common pathway. So what we're doing is we just get to factor 10. Those complexes, tissue factor 7 and 9 and 8, they complex, they get to factor 10. And both of those, both pathways respond to the vessel injury. It's just that extrinsic is faster. I would also write in your notes platelet factor 3. I didn't mention it on my board notes, but write it in your notes so you know that that's also essential. PF3, platelet factor 3, along with the calcium ions are needed for these processes. Again, here's that picture I showed you earlier, the fibrin mesh on the white threads. When it traps the blood cells, we call that the coagulation. I'll pick it up here next time. I have a meeting to get to. But before you guys leave, I do have some announcements, so keep your ears peeled for a couple minutes.